Good morning, class. Mr. Carver here. Here's a gigantic warm-up, one that would take probably 45 minutes in class if you were here. All right, hit pause, work them if you like, and then I'm going to work them immediately, and then you can hit play and see how you did. All right, as if by magic, the red is the answers. The red answers are the answers to 1 through 6. The one that may be a little tricky is number 5 there. Remember that the arctan of a negative number has to be in either Q2 or Q4. Has to be in Q4 because of the range of the arctangent. So I'm going to negative pi over 4. That's the only way I can get into quadrant 4 without going past the boundaries of negative pi over 2 to pi over 2. Okay. Number 7. I think the first thing I would do is break this apart to make this a little bit easier. So I've got y prime, not y prime. I've got y is equal to 1/2 log base 4 of x, because that's positive, it's coming from the top. And this exponent of 1/2 comes down to the front. And then minus, because the rest is coming from the denominator, that is 1/3 log base 4 of x squared plus 4. So my y prime then is going to be equal to just the derivative of each one individually. The first one is 1/2 because it's a constant multiple rule. Remember, it's just constant times the derivative of this. That is going to be 1 over ln 4 times 1 over x times 1. So it's 1 over the natural log of the base times 1 over what I'm logging times the derivative of what I'm logging minus another constant multiple. That's 1/3. This is 1 over the natural log of the base, 1 over what I'm logging times the derivative of what I'm logging. This then is the unsimplified version of the derivative of number 7. All right, let me make some room here. All right, and we'll do number 8. So you got 2 choices for you, as I see it, maybe x plus 1 or x minus 2. I think you should always start with the denominator. By the way, this is top heavy, so if you multiplied out the top and did long division, you will get the same answer. Another way to do it is to, let's see here, let's cordon this off here. If there's enough room there, I'm going to let u equal the denominator. And then my du is just equal to dx. But I also see that this line is easily solved, so x is equal to u plus 2, and then I can use this right here to fill in for the x's on the top. So this will give me the integral of x, which is u plus 2, times x plus 1, that is u plus 2 plus 1, that is all over just u, times du. That is u plus 2 times u plus 3 all over u du. And again, I'm just plugging this u plus 2 into here and there. So here's my x plus 1. Now I'm going to FOIL that out. That puts me right here. This is the integral of u squared plus 5u plus 6 all over u. I'll bring the u up to the top and distribute. That gives me u to the first, plus 5, because that gives you u to the 0, plus 6u to the negative 1 du. Just a little more room here. And now I can integrate each one of these individually. This gives me 1/2 u squared plus 5 times u plus 6 times the natural log of the absolute value of u plus c. And then, of course, I'd like you to take this u, x minus 2, and plug it here, here, and there, which would be your final answer. All right. So today is 5.8, and this is arc trig functions, just like what we worked on yesterday. And what we're going to do is we're going to derive. This is differentiation. means finding the derivative of arc trig functions. So what I'm going to do is I'm going to give you the formulas, show you how to use them, and then at the very end, I'm going to show you where some of these came from. So if you're interested in seeing how they are derived, just keep the video playing and you'll see it at the end. All right, so if you were in class, I would have you put this into a memorize box. Because these are good to have in your brain for later on in calculus. Now, these derivatives are all going to be chain rule derivatives, which is why they're using u instead of x. So u stands for any differentiable function of x. This is not u substitution, like for integration. This is just the chain rule. So the first, if I derive with respect to x the arc sine of u, that gives me 1 over the square root of 1 minus u squared times u prime. The second, the derivative with respect to x of the tangent, arctangent of u, is equal to 1 over 1 plus u squared times u prime. The derivative with respect to x of the secant of u turns out to be 1 over the absolute value of u times the square root of u squared minus 1 times u prime. So that's the derivatives for the arcsine, arctan, and arcsecant. That's not the secant, that's the arcsecant, Mr. Carver. The derivatives then for the cofunctions, and we mentioned this earlier on in the semester, cofunctions are negative. So the nice thing about this is that the cofunctions are just the negative values of these three. All right, so to save a little time, I've already filled those in, but you'll notice that the sine and the cosine are exactly the same, except the cosine is negative. Ditto for the tangent and the cotangent, the secant and the cosecant. Those are all arc functions. The cofunctions are all negative. A couple of things about this that are a little confusing, and again, you can pause this to get that down in your notes if you like, is that order makes a difference. Like, for instance, if you look at 1 minus u squared, that is very different from u squared minus 1, obviously. Here's the way I remember it. Well, other than just memorizing the formulas, the order gets a little confusing. So I think about these u's wanting to be close together, which is why the u squared comes first underneath the radical. There is no u out here, so it just comes second. It's the opposite of the ones that are close together. And then, of course, for the arctan, 1 plus u squared, order makes absolutely no difference. I don't care how you write it. So that one doesn't matter. All right, let me show you how to use these. Let's say, for instance, that I've got y is equal to the arc sine of negative 3x squared. And I want to derive that. Again, this is the chain rule, so this is my u value in here, the innermost function. Working from the chain rule, you want to work the outermost to the innermost. So first I'm deriving the arc sine of something. And when I do the arc sine of something, what I want to do is I want to take the derivative of just the arc sine, and I'm going to use the formula. So my y prime is equal to 1 over the square root of 1 minus u, and in this case u is negative 3x squared, so it's negative 3x squared, and then I want to square that. That is then times the derivative of what I'm arc sining. So it's this right here. This is the derivative of the innermost function. That turns out to be negative 6x to the first. So if you were to clean this up, probably not going to have you simplify this, but then your y prime is going to be equal to negative 6x on the top. This is the square root of 1 minus 9x to the fourth. So it's important to keep in mind that what you're deriving here is the derivative of the innermost function. It is not that right there. You're not deriving that, you're deriving what you're arc sining. So always go back to the original function to determine what that portion is right there. All right, they're going to mix in these new derivative rules with all the old derivative rules. So you've got to be careful here. Let's say, for instance, I've got y is equal to the secant of root x times the tangent of root x. Now remember, we're deriving this because this is the derivative of something. We're actually deriving this. So this is a product. I need to use the product rule. So y prime is going to be equal to, let's derive this first, and then we will not derive the second. So arcsecant. Back up here a little bit and make these arcs. I don't want to have regular secants and tangents. So it's arcsecant of root x times the arctangent of x. Okay, so the arcsecant of x, if you're looking at the formula on your notes there, this is going to be 1 over the absolute value of the square root of x. Now, I understand that the square root of x is always positive. The absolute value is a bit redundant, but go ahead and throw it on there anyway. This is then times the square root of, this is root x squared. It is what you're arc signing squared, minus 1, times the derivative of what I'm arc signing. And I'm arc signing this part right here. And we already know that we've done this many, many times. I don't like orange. Let's go back to here. This is going to be 1 over 2 times the square root of x. That's the derivative of this portion right there. Remember, you multiply that then by the arctan of root x. And then I want to add to that the reverse. So now what I'm going to do is I'm going to work with just the second part. So I'm going to derive this part. So let's go ahead and fill in just the first portion there. That is the arcsecant of root x. And now let's derive the red portion. So arctangent of x. This will be times 1 over 1 plus root x, the quantity squared, which turns out to just be squared. But again, I'm not simplifying this. Times then the derivative of what I'm arctangenting, which is this right here. And that is 1. I don't like orange. This is then 1 over 2 root x. Why don't I like oranges, you might ask? Well, when I was in college, I worked at an orange juice factory. Was fired. Couldn't concentrate. This then is the product rule derivative of my original function, unsimplified. And I was also fired because my face kept peeling. Actually, that's why I was hired, and the fact that I had a navel. All right, let's mix it up with some old stuff. So what if I've got y is equal to, let's do log base 2 of the square root of 3x squared plus 1 times, let's do the arc cosine of e to the 2x. Let's go ahead and make it horrible. All right, so again, product rule. So I've got y prime is equal to the derivative of the first, which is 1 over ln2, 1 over the natural log of the base. In fact, let's do this. Let's take the 1/2 from the radical and move it out to the front, make it a little easier to do. So I've got a 2 then out front. That's 1/2 times 1 over the natural log of the base times 1 over what I'm logging. So now this is gone. There we go. So it's 1 over 3x squared plus 1 times the derivative of what I'm logging. That's 6x. So all that is just from previous sections in Chapter 5. That all then times the arc cosine of e to the 2x. And then again, I want to switch it up. So I'm going to have the first as is. That is log base 2 of 3x squared plus 1 times the derivative of the arc cosine, which is negative 1 over the square root of 1 minus e to the 2x squared times the derivative of what I'm arc cosining, that stuff right there, which is e to the 2x times 2. Now, some of you may put a natural log of e in there. That's totally okay. That's just 1. You can put it in. You don't need to put it in at all. This then is my derivative of that product rule right there. All right, last one. Then I'll let you guys go. How about y is equal to the tangent of the arc sine of 3x. So this is chain within chain within chain, not a product rule because I'm tangenting all of this. So again, I'm working outside in. So, and this, by the way, is not the arctan, it's actually the tangent. So my y prime is going to be equal to the derivative of the tangent of something. That goes to secant squared of the something Don't derive the something yet. Now, I'm done with that, so I'm going to keep track of what I've already derived. I get rid of the tangent. Now I go inside. It's the arc sine of something. So that formula is 1 over the square root of 1 minus what I'm arc sining squared. Done with that, times the derivative of what I'm arc sining. And now I'm finally done with that. That entire string of things, and by the way, I am only arc secanting this first part here. So this, you can group this separately. It is the product between those two. That then is my chain rule derivative for the tangent of the arc sine of 3x. All right. That's all I got for today. You can look at my calendar to see the assignment. I'm going to spend a couple more minutes just talking about where these formulas come from. If you're interested in watching, go for it. If not, believe me, I'll understand. So I think I'll work through two of them. One of them, I'm just going to show you where like the derivative of the arc sine comes from, and then I'll spend some time talking about the arc secant because it looks weird, it's complex, it's got an absolute value in it, and you might be wondering why that is. So we'll talk about that. So what I'm going to do is, I'm going to start off just by using this expression, y is equal to the arc sine of x, and we're going to derive this, but let's just assume that I don't know the formula. So what I'm going to do is, just like we do in trig, I'm going to bring this sign over here. I'm going to sine both sides. So the sine and the arc sine cancel. This gives me the sine of y is equal to x. And you used to do that back in the day in trig all the time. But now it's not so bad. Because I can derive this. So I've got the sine of y, which turns out to be the cosine of y times 1 dy over dx, because I'm implicitly deriving. This is equal to x. That's not equal to x. That's equal to 1, excuse me, the derivative of x. All right, and then what I want to do is I'm going to divide both sides by the cosine of y. So dy over dx is equal to 1 over the cosine of y. Okay, so it's this formula right here that I need to take a look at. So check this out. I want to get rid of part of this, and here's how I'm going to do it. I go back to my original formula here. Y is equal to the arc sine of x. And remember that this is the ratio, this is the angle. So what I'm going to do is I'm going to draw a triangle in quadrant 1. And this ratio is x over 1. And I can also see that here, right? The sine of y angle is equal to x over 1, which is the opposite over the hypotenuse. So that part is x, that part is 1. Using the Pythagorean theorem then, this side, missing side right here, will be the square root of 1 minus x squared. And this is my angle y. So if I use this triangle to substitute the expression for the cosine of y, I get dy over dx is equal to 1 over the cosine of this angle, which is adjacent, the square root of 1 minus x squared, over the hypotenuse. Copy dot flop that, I get dy over dx is equal to 1 over the square root of 1 minus x squared, and I'll write it like that just so you can see what I'm doing, times 1. So this is 1 over the square root of 1 minus what I'm arc sining, which is x, times the derivative of what I'm arc sining, which is 1. And you can see where that formula comes from. So this is my u value here. This is my u prime. All right, let's take a look at the arc secant. A similar process can be used with y is equal to the arc secant of x. So again, if I bring the secant, arc secant, or if I secant rather both sides, I get the secant of y is equal to x. And now if I drive the left-hand side, I get the secant of y, tangent of y, dy over dx is equal to 1. So my dy over dx, if I solve for it, gives me 1 over the secant of y, tangent of y. All right, and again, if I look at this, this is the secant of y. Here is my angle y, if I create a right triangle. Secant is hypotenuse over adjacent, so this is x over 1. Using the Pythagorean theorem, this turns out to be the square root of x squared minus 1. And then if I use this triangle to substitute into this expression here, I get 1 over the secant of y, which is hypotenuse over adjacent, times the tangent of y, which is opposite over adjacent. So if I'm deriving the arcsecant of y, I get this formula because it is 1 over absolute value of what I'm arcsecanting times the square root of what I'm arcsecanting squared minus 1 times the derivative of what I'm arcsecanting. So in the next page, I'm going to show you where this comes from, why that's positive. Okay, so the derivative of the arcsecant turns out to be 1 over the absolute value of u times the square root of u squared minus 1 times u prime. And to use a slightly easier example, let's just do y is equal to the arcsecant of x. We'll just use x, and I'll show you what happens when you change it. My y prime then is equal to 1 over the absolute value of x times the square root of x squared minus 1 times 1. So if I look at the graph of the arcsecant of x, you can see it here in red. So that is a graph of the arcsecant, which is a flip of, there we go, which is a flip of the original secant graph, which you can see right here. In blue. I'm going to see if I can do this without it moving. So the regular secant graph with a restricted domain from 0 to pi, not including pi over 2, this is pi over 2 right here, the vertical asymptote. So it's the red graph that I'm looking at. And what you'll notice here is that the arcsecant graph in red always has a positive slope. And if you also recall, the derivative is the slope machine for this curve right here. That curve always has a positive slope, which is why you're absolute valuing this. Now, let me show you another way to look at it, because this doesn't prove why it needs to be positive. If I have a different example, for instance, let me change this just slightly. Let's get rid of all of this. And let's say that I have then the arcsecant of negative x squared. What that's going to do then, this negative value, actually let me just change this a little bit so it's a little even easier to see. Let's just do negative x. So if you recall from stretching and shifting back in pre-calc and the beginning actually of this year, this negative sign actually flips it over the y-axis. So now it's going to look like this. You can kind of visualize that. And what you have is negative slope everywhere. So check this out. If I have y prime and I have 1 over the absolute value of negative x, this gives me the square root of negative x squared minus 1 times the derivative of that. That gives me negative 1. The slope of this black line, or of this red line right here, of the arcsecant flipped over the y-axis, is always negative. This is my slope machine. This will make it negative. This has to be absolute valued, otherwise you would get positive slope. So you're absolute valuing what you're arcsecanting here. This turns this always into positive, and then this gives you control over what the actual slope is. So without this absolute value, you would have the incorrect slope. So it's an adaptation or an add-on that they put on to make sure that the slope machine does work for the arcsecant. There you go. All right, guys, good luck with the homework. Thanks for hanging in, and we'll talk with you soon.